Welcome everyone to our distinguished lecture for the College of Engineering. This might be our fifth, I don't care, I've lost count now. This is a wonderful event which celebrates a distinguished senior faculty member who has had a massive impact, not only scientifically and technologically in their field, but also a major impact on the institution and the branding and what makes it differentiator for Boston University's College of Engineering. It's a celebration of that impact and a celebration of the way we honor our leading faculty members. Today's speaker is Tom Bifano, who directs the Boston University Photonics Center. He leads its programs for education, scholarly research, and development of photonic technology translation for commercial and military applications. Tom received his bachelor's and his master's from Duke in mechanical engineering and material science, and his PhD from NC State in mechanical engineering. He joined Boston University in 1988 as an assistant professor. He serves on the U.S. Army Science Board and is founder and chief technical officer of Boston Micro Machines Corporations in Cambridge, Massachusetts. Tom's research focuses on design and manufacturing of micro-electromechanical systems, MEMS, for optical applications. He was awarded the International Bepi Colombo Prize in 2009 for his achievements in research, education, and technology development related to deformable mirror development and space science. He has won R&D Magazine's Top 100 Innovator Awards on 3 separate occasions. That's 3 separate years. Tom has over 120 peer-reviewed journal articles and conference proceedings, 6 issued patents, and has served as the plenary speaker for several major meetings, including the SPIE and Optical Society of America conferences. Locally, Tom's impact has been nothing short of sensational. He served as chair of the Manufacturing Engineering Department for 7 years, which happened to be simultaneously with my tenure as chair of the Biomedical Engineering Department, which was helpful to me in many ways. And during that time, Tom worked with extraordinary collegiality as a critical advisor as we put together, for example, the university's Whitaker Foundation Award. To be specific, it was Tom's vision to add a component to that award in biomems, to the proposal that made it competitive in our capacity to recruit excellent faculty, including, of course, people like Kathy Clapperich here at BU. As the second director of the Photonics Center, his impact has been absolutely transformational. It is Tom's leadership and vision that made the Photonics Center become such an enjoyable and enabling research and education amplifier for not only engineering, but for chemistry and physics at Boston University. The center is now one of the most powerful magnets for excellent faculty and excellent graduate students. It's nothing short of the pride and joy of the faculty and administrators throughout Boston University, and Tom has made this happen. Finally, on a more personal note, Tom and I have been friends and close colleagues now for 25 years. He is a confidant and a crucial advisor to me as chair, and again as dean. Perhaps his most important role was serving on the Dean Search Committee, which found me. Please welcome one of my favorite lunch partners, Professor Tom Bifano.
Thank you, Ken. Thanks, that's great. I consider that my finest moment as well. And there were 5, so I'm the 6th. Irving told me I had to correct you. So thank you all. I'm so delighted to have you here, and this is really special. It's wonderful for me. I'm really moved. I love being at BU, and I love having you as colleagues. So I'm grateful to be able to tell you a little about what I do. I'll share some of my experiences here, and then we'll try to get it over with mercifully. So this painting, a lot of people have asked me about this painting. This is Guido Sandri, of course. Those of you who have seen Guido Sandri paintings around, this is classic Guido Sandri. Guido is was a professor in mechanical engineering when I first arrived at BU. With my wife, we were both professors in the College of Engineering, started here, and Guido was a wonderful, wonderful mentor for us in the first few years we were here. He was great, and he had this great sense of both science and math, but also of art. He calls this optical brutalism, and I think you can agree. And this painting is actually in my house. So, so my wife and I invited Guido over to dinner one night, and he said he would paint us a mural because we had a big, big blank wall and a great cathedral ceiling, 18 feet by 6 feet or so. And Guido said, no problem, buy me a canvas, buy me these paints. And he gave me the numbers of the paints, and we bought the paints. And he came over, and we drank a bottle of wine, and we had some beautiful dinner, and we drank some more wine. And my daughter is there. My young daughter is playing with Guido. Everybody's having fun. And my wife comes over to me and says, you know, it's getting kind of late. When's he going to paint the painting? So I go over to Guido and I say, Guido, you know, it's about 10 o'clock. When are you going to get started painting? He says, oh, I could never paint while you're awake. Good night, Guido. We put the kid to bed. And you hear, and the canvas was on the ground, and you hear just swooshing all night long, this swooshing. So nobody's sleeping. I'm not sleeping. My wife's not sleeping. The kid's not sleeping. But and then it gets quiet. And I think, oh, thank God, he's done. And I come downstairs, and he's reading poetry on the couch, on my couch. And I said, God, it's beautiful, Guido. At this time, there's no black in this painting. And he says, oh, I'm just on a break. I'm looking for inspiration. And then through the course of the night, he finished it, and then the final touch was he had my daughter walk all over it in her sneakers. So when you look on this, there are all these footprints. So I dedicate this talk to Guido, who's still with us, but is now no longer an active member of the department. Okay, quick tour of my life at BU. This guy, of course, this is Dan Udelson. He had the grace to hire my wife and myself to this university. And for those of you who know me well, like Ken, I've told the story many, many times that they really wanted my wife. They really did. And Dan said to me, look, Tom, there's 50 other universities in the Boston area. Can't you find a job at any of them? And he was kind enough when I couldn't to hire me. And Cal, who's taken pictures, is always reminding me that when I first came, I had to try to change from being a graduate student. And the first thing I did was buy a whole bunch of bow ties. So that for the first 3 years I was here, it was all bow ties, nothing but bow ties. So that's me, and of course hair. I had done grinding on my way in. So I used to do grinding of glass. That was what my PhD was in. And I had this particular idea about how you could grind glass without making a fracture, make it a ductile chip on glass. And we did that. It was beautiful. And so that was what I started doing my research in. I got a grant when I got here and from the NSF to do that again and to try to make grinding wheels last a long time. So I got the grant, and I finally figured out sometime, I think, I don't know, 5 years in, how to make grinding wheels last a long time. So this is the grinding wheel that lasts a long time. These are the ones that don't. Brilliant, beautiful insight. Take it to Norton, which is now Saint-Gobain in Worcester, and I took it to them. I said, I've solved your problems. And they said, this doesn't solve our problems. We sell grinding wheels. And so I got out of that. This is so I really did. I just said, I'm done with grinding. I'm done with glass. I got to figure out what else to do. And right at that time, you look at these names, Bennett Goldberg, Gil Jones, Ted Moustakis, Ken Rothschild, Mike Ruane. 3 are still active faculty. 2 are emeritus faculty here, all pioneers in the Photonics Center. They wrote this proposal that got us $29 million. John Silber signed it, and that's what established this building. So I became a part of the Photonics Center due to their great work. And then I started working on this thing. I had an idea about how to make compact discs more efficiently. And I had this idea, and I launched a company, and it was a great idea, way ahead of its time. And that failed very badly. And then I was the chair of manufacturing, so I was looking for a picture to show what it is to be the chair of manufacturing. This is the class of, I think, for the manufacturing engineers, maybe 2003, 5. Yeah, so that was the class. We used to take class pictures with the gang. They were small enough we could take them all in there for the senior class. And that was a wonderful part of my life. And then I started making MEMS. And I started making MEMS because we hired a guy. I'll tell you about him in a minute. But we hired a guy who was doing MEMS, and he said, yeah, anybody can do this. This is really easy. And so I started making the MEMS. And then, just a month ago, I got my clock. So for those of you who haven't been here long enough, 25 years, you get one of these. It really is about that size. And so that's it. That's the introduction. That's who I am for 25 years. Okay, so let's move on to the talk. The MEMS. I've developed over the last maybe, I guess it's about now 15 years, both an academic program and in concert with that, a commercial program, a technology development program at a company. So that's unusual for a faculty member. Lots of potential for conflicts of interest, lots of seedy things that can be thought of about it, but it was wonderful for me because it allowed everything I did academically to be aimed toward technology translation. This guy's in the back now. That's Paul Bearden. He was my wife's advisee in the EK 100 class when we first got here. And I liked him immediately because when we invited all the students to our house for pizza, we lived out in Brookline, Paul was the only one who came. So it was awkward for him. It was awkward for us. But we've been close friends ever since. And this is Stephen Cornelissen, who's the vice president of the company. There are about 10 people in the company, and I think maybe 6 or 7 BU people have worked there through the years, and 3 or 4 work there now. So we developed this company, and it's all about this thing on the bottom here, which is a cross-section of a silicon mirror. This is a silicon substrate. All these parts are silicon. They're color-coded because they're different parts of the mirror, but these red things are fixed electrodes. The blue things are an electrostatic actuator array. The green things are posts, and the orange thing's a mirror. And the whole idea is that if you apply a voltage to one of these electrodes, the actuator, the electrostatic attraction between positive electrode and the grounded actuator layer pulls those two plates together. That pulls on the post, that deforms the mirror. Voila, you have a deformable mirror, so you can make something change. And I'll show you how we've milked that to death. That particular geometry, we have done nothing innovative since then. I'm not sure that was even my idea. I think mostly that design was a collaboration between me and Ken Gabriel, but I have certainly claimed credit for it everywhere outside of here. So one of the things I wanted to, I guess you already have the impression that we have a certain philosophy in my group and with my graduate students, and I was trying to find a slide that represented that, and I got one. It's off the web, so this is not an original thing, but I laughed out loud when I saw it, so I wanted to give it to you. But this is the philosophy of my lab. I'll give you a minute. So the idea is there's only 2 things in the world that matter to a mechanical engineer. It's WD-40 and duct tape. Does it move? No. Should it? Yes. Put some WD-40 and the other way around with the duct tape. But the problem we're trying to solve, the problem that we took on related to this. So in the very beginning, the adaptive optics, these deformable mirrors, the problem is that the leading causes of blindness are diseases that affect the cells in the retina. And to make progress on those diseases, you really need to be able to see the cells in the retina. And it might seem strange to you, but until 4 or 5 years ago, that was impossible to do while you were still alive and had your corneas intact. Right? We could take your retina out and look at it, but we couldn't see the cells while it was still in your head. So this is the problem. And many, many mistakes were made by God on creating eyes. So many. One of them is that the cones and the rods are behind the blood vessels, behind the nerve fiber layer. They're laying underneath everything, these things that are supposed to detect light. And so, so I drew this the wrong way for years, thinking the cones have to be in the front, don't they? And my ophthalmology friends always tell me, no, they're back there behind all the nerves. So that's a problem, that they're actually buried a little underneath things, and their sizes are about 2 microns or 3 microns in lateral span, which makes them impossible to see. So this is the, for those of you, many of you are my colleagues in engineering, and some of you I'm so grateful for are not engineering or science people, just come because they like me for one reason or another. So I wanted to give my quick tutorial. So for those of you who are photonics members, forgive me. For the rest of you, thanks for coming. So you got a lens, and the lens goes to a focus, and that's the ray optics idea, and everything is wonderful there. And if you think about the lens having a focal length f, and you think about the width of that beam that's going into the lens, and you ask, well, what does it actually look like? What does the intensity look like at the focus of the lens? It has a certain width to it. We call that an Airy spot, and if it's a circular aperture, and the width is this dr. Okay, and I would say God gave us this equation, but it's actually Germans who gave us this equation about the and there are some similarities about the diffraction limit. So the thing about the diffraction limit that I find wonderful is that it was so dominant as the you can't break the diffraction limit, which sort of felt good to my German colleagues for many years. And now, if everything published in photonics literature is all about, I broke the diffraction limit. So there really is no diffraction limit, right? So this is just a notional idea that if you do take a lens like this and focus it down, that this dr is just a function of the wavelength, the focal length, and the aperture diameter of the lens. And if you use this simple system, that actually works out to be true. So then, if you think about, well, let's make this an eye. All we had to do is draw a circle around it to make it an eye. And now, for human eyes, lambda's 500 nanometers. That's visible light. F is 20 millimeters. D is 5 millimeters. And so you can make a pretty quick estimate of what the diffraction limit is on the back of your eye. So if everything was great, we'd be able to see those cells, because they're a little bit bigger than 2 microns. So, but we can't see the cells. So then you ask the question, well, why can't we? So we have to figure out what our imaging resolution limit is. And there's a really easy way to do that. So what we're trying to find out is, what can we actually resolve on our retina? And the way to do that is to take 2 lights that are far away and walk back away from them until you can't see that there's 2 anymore. And when you can't see there's 2 anymore, you just do the geometry of these 2 similar triangles, and it'll tell you what the actual spacing is you could see on your retina. So no fancy tools, just this. And so we have that. That's over here. So this thing over on the wall is 2 LEDs, 2 green LEDs. They're blinking. You see them? So raise your hand if you can see 2. Now, don't cheat. If you can see 2, raise your hand. Right? Okay, so keep them up just for a second. So some of you are blind, but it's about here, right? So it's, De Winter, you lie. This is like the Letterman band, yeah? So this right here is, you can put them down now. So that's 4 each of these columns is 4 meters away. So it's 1, 2, 3, 4 times 4, 16 meters. And so we got L is 16 meters, and D0 is a centimeter. They're about a centimeter apart. And of course, I didn't do this thing without calculating that in advance. So it's about 10 microns, maybe 15, 10 or 15 microns on the retina. That's the problem. That's bigger than all the cells. So this is a great scientific opportunity and also a great technical opportunity for us, because if we can fix this problem, it's not just that we make it better. We make it better to where there's some functional thing you can see that you couldn't see before. So that's the idea. Now, why is there the difference between the theoretical diffraction limit of 2.4 and the actual? Well, you know that has to do with these bad optics we've got. So the optics in your eye, I'm fond of saying they're like Cracker Jack lenses, because not only does that tell you what it is, but it also differentiates if you're over 50 or not. When they used to put the lenses in the Cracker Jacks. Bishop knows. All right, so the imaging diffraction limit is this. What actually happens is your lens is a little bit warped. The warping spreads that diffraction limit to something else. And the whole point of adaptive optics, of deformable mirrors, is I can compensate the aberrations. So the aberrations are here. They're spreading this thing out. If I put a shape on the DM that makes these lines past the lens line up again, then I get back to the diffraction limit. That's all adaptive optics is. That's all we do. And so the simple question is, so when you do that, you get a nice, sharper image. The simple issue is, how do I measure those aberrations, and then how do I fix them? So this is what your eye, we can take all the aberrations in your eye and decompose them into orthogonal components, and the doctor does that for you when you get glasses. They tell you have cylinder, which is astigmatism, and an angle, a rotational angle on astigmatism, and you have defocus, and they fix that. None of these other things do they fix. But these are what they look like if you have those aberrations in your eye. I've got some of this, which is spherical aberration. That's halos around things. If you look at the sky at night, and you look at a star, and you see each star has a little halo, he really doesn't have a halo. If you have these, they call these coma aberrations because of what they do to your eye. It looks like a comet. So if you look up at the star and it looks like it has a tail. Again, it doesn't really have that. So then what do you do to fix them? It's a really simple system. You have light from the eye that you either put in there yourself or, well, you have to put it in the eye. You send light in, and then the light that comes back out, you bounce it off the deformable mirror, and you also bounce it off of a wavefront sensor. What's a wavefront sensor? It's something that can tell me the shape of the wavefront error, the shape that I need to put on my DM. And so once it tells me that, I put that on the deformable mirror, and I get a high-resolution image. Okay, so why MEMS DMs? Why not do this some other way? Well, before MEMS DMs, you could still get deformable mirrors. There are these guys with, they'd make nice glass plates, and they'd take piezoelectric actuators and glue them to the back of the glass plate. They did this here in Massachusetts. Actually, iTech was the company, and it was a spin-out of BU. And they make great deformable mirrors. So this is one that is, it's in a large telescope. I'm not sure which one. I could make it up, but then Paul would know I was lying. But it's a large mirror. It's got a couple hundred actuators in it. But for this mirror, each actuator and driver ends up costing you about $3,000. So you do the math. If you've got 300 actuators in this thing, you're getting close to $10 million for a mirror. You've got a mirror that's very, very expensive. So this is a problem for people who want, and it's also not exactly the size of the eye. It's 100 millimeters. So we made these mirrors. They have a tremendous design advantage in that we can scale them to large arrays. They're made with MEMS. They're smaller in size, weight, and power. They're lower cost. We can make this same number of actuators for maybe $10,000 or $15,000, and okay, maybe $50,000. And then they have this performance advantage that they're not piezoelectric, so they're creep-free, they're fast, and I think I said low power twice. Okay, so how did we decide then to make these MEMS? Why did I, so I'm grinding glass, right? I'm grinding glass. There are all sorts of materials, things you could go into. Why do you go into MEMS? So I'll tell you quickly how that happened for me. This is all around the early 90s. There was a foundry. They came up with the first MEMS foundry. So you could send them a design, and they'd send you back a MEMS device. In North Carolina was the foundry. This is great because it used to be only electrical engineers had these tools. And electrical engineers, they're nice. They're not that friendly with their tools. So mechanical engineers had to go in and say, can I borrow your lithography tools? Can I borrow your thin film deposition? And then you had to learn how to use those things. Nobody wanted to do that. So the mechanical engineers were loving this foundry. And the foundry was an idea of a mechanical engineer. So this opened the sandbox to MEs like me. And then they launched exactly at the same time this DARPA MEMS program. And the DARPA MEMS program was launched by this guy, Ken Gabriel, who for 8 weeks was a BU professor. And he was a BU professor here. He was great. He was wonderful. And as soon as he got here, he got an IPA, an appointment to be a federal program leader, a contract monitor at DARPA, and he took that job. And before he left here, though, in those 8 weeks, he and I wrote a proposal together for deformable mirrors, to make deformable mirrors. So it was a joint idea. And then when he got to DARPA, our proposal was rejected by NSF very badly. Comments like, "Ugh." And so he calls me and he says, I'm now at DARPA. And I said, yeah, I know, your proposal with me didn't get funded. And he says, no, but you didn't hear me. I'm now at DARPA. And so he said, submit that thing to me. And I did. And I swear to God, he called me, and I submitted it. It was a beautiful proposal. I submitted it to him, and he calls me, and he says, what? You submitted this with an NSF kind of budget. This is DARPA. Double it. And I said, okay. And I added a few tasks, and it was wonderful. It was really the launch of a great thing for me. And why did he and I choose adaptive optics as the topic? Because in 1991, the Department of Defense declassified adaptive optics. And so for those of you who are really brilliant and have ideas all the time, you're always way ahead of the rest of us, right? So you have in the back of your mind all these things going on. Oh, I could try that and I could try this. But for me, it was great to have this moment where the Department of Defense just dumped a trove of material out. So now I'm the equal of everybody else. I know what everybody else knows all at the same time. And so we all competed for who can make the best use of this suddenly declassified material. And I should say that when I did this, there was one other person in the college who saw this as a great idea too, and who joined me on this thing with DARPA, and that was Dave Castagnon. And Dave Castagnon was at the time working on small macro-scale deformable mirrors, and for him and I, it was just a watershed of an event that DARPA wanted us to do this and wanted us to do it in this area of importance to DoD. So we had this great trove of activities. Okay, so now let me go through the design and the fabrication of the MEMS. The first publication we had, here's with Dave, and Mark Hornstein, and then a bunch of students, was about how we make these deformable mirrors. Okay? The actuators, I've said, are electrostatic. So that means essentially you can think of them as parallel plates attracted to one another. And those parallel plates attracting to one another cause this deflection. The electromechanics are pretty straightforward. There's and one of my students recently did his PhD work on this. He realized that if you just pull the mirror off and the posts, you have a completely linear system, a beautiful linear system that's a plate defined by the plate equation. And what he understood that I didn't understand until he told me was, we don't have to solve this plate equation. We're going to tell it what deflections we want. We're telling it the part with the del on it. So all we need to do is figure out what the forces are. So this is an integration. All we have to do is integrate this equation. If we integrate this equation, we can find these forces. Okay, now you got the forces on the post. So what? I need to know what voltages to apply to the electrostatic actuator. So he says, well, okay, I've got this equation over here where if you give me the forces and again you give me the deflection, again I can solve just almost algebraically for the voltage. And so this student had this great insight, and we managed then to get a beautiful model of the device and be able to control it in open loop very nicely. So then we made a version of it that I could understand because it was simpler, where you just cut the mirror. And now there's no coupling in the mirror at all, and it's just this last part that you have to worry about. And that's an even easier set of equations to work on. Some people want segmented DMs and some want continuous. I'll tell you a little about that. And then, Ken asked me to be part of the Kern lectures. So then I had to actually go back and solve all those horrible equations. And Dr. Barboni was nice enough to let me in his class. And of course, I spent months making sure there were no mistakes in the equations. And then I talked to the students as if I had done it that afternoon. All right, how do I make them? So you make them in this recipe-based process. You go in, you say, I want to start with a silicon wafer with a nitride layer on it. I want to deposit a little bit of silicon there, which is my bottom electrode. I'm going to deposit oxide, silicon dioxide, which is my sacrificial material, on top of that first electrode I made. I'm going to deposit more silicon on top of that. And you'll notice each layer I deposit is conformal. It goes on to the next one and covers it up. So you could be saying to yourself, well, that's a dumb way to make a mirror, that, you know, when you finally get up to the top, this thing's not going to be flat. Yeah, that's a problem. And then you cut holes in the silicon so that you can get at this oxide, and then you pour hydrofluoric acid on the top of the whole thing, and it eats away the oxide. And then you're left with this actuator, and then the actuator behaves sort of like this when you put voltage on it. So this is just the actuator part. I'm going to now put a post in the middle of that actuator and attach it to a mirror at the top. Oh, I got to say, once I figured out that part, I started using these making MEMS devices in my classes. And at first we made really complicated MEMS devices, but I realized what they really wanted was to write letters home to their parents in tiny letters, too tiny for their parents to see. So that's what we did. We did all the lithography, but not released structures. What we did was we used this class to write these 20 nanometer tall letters on a 3 millimeter chip home. I'll give you an example here. When I was putting this slideshow together, I was digging through last year's class, and I found this one. It cracked me up. It says, "Hi, Mom, loving be you so much. I've neglected to bathe. Kevin." He was not a good student. All right. So what else do we do? Now I've got the actuator layer. We've been to the actuator. We then do another layer to get the mirror and post on there, and then we dump the whole thing in the acid. And then BMC has developed a whole bunch of processes. None of those were really developed at BU to put gold on it, put it in a package, seal it up, and evaluate and test it. Every time we do a batch, it costs us somewhere in the neighborhood of $250,000. And the batch gives us 20 wafers and 3 to 100 devices per wafer, depending on how big the device is. And so we have had full batches that produced nothing, and then we've had full batches that produced the world's supply of a particular kind of mirror for indefinite time. So the first time we really got a fully working, open loop, everything going mirrors about in 2007. Somewhere a few years before that, people from around the country started wanting to buy these mirrors, even though they were not very good at that time. And we're grateful to them because that kept the company alive. So they were buying mirrors that were horrible, knowing that by sustaining us, they might be able to eventually get good mirrors. And that did work out for them. The mirrors are reliable. We've tested them to trillions and trillions of cycles, so some mirrors to 50 trillion cycles. There's really no failure mechanism. If it works out of the gate, it's going to work forever. They're really fast, so we can do frame rates of 20 or 30 kilohertz with these things. That changes the world of adaptive optics in some way, because you don't have to be as smart if you can be fast. That's at least what I said to the kids in school. Yeah, this is, they're very predictable. This is, again, the student who figured out if you just anchor everything at the post, it's just a force balance. The upper part is linear, the bottom part is calibratable, and so you're in good shape. And so we now can, in a single step, get them to go wherever we want within about 20 nanometers. And then the two characteristics that are really important about the MEMS DMs are their stroke, how far can it move, and how many actuators does it have. And so these are the two columns sort of as a function of time, how we did over the years. You could see sort of a steady increase with the demand coming from the market for more actuators and larger stroke, not always at the same time. And then these are two of the application areas. I'll tell you a little more about those, ophthalmoscope and telescope. So ophthalmoscopes need more stroke, telescopes need more actuators. And then one thing we learned late, and it's embarrassing because I was chair of the manufacturing engineering department, is some things about yield. And this was truly a revelation for me. It shouldn't have been, but it was. So we're making mirrors, and we're making, these are the bread and butter mirrors we make. And they're coming out, you know, great. We're making 90% yield. These things are coming out great. So somebody wants a mirror with larger number of actuators. And we're using the same process, which means we have the same defect density per square centimeter. So let's make a mirror with a little bit more actuators. It's not a big deal. It's no problem. So then we got, people came to us to make a mirror that's 4 times bigger than this. I'm saying, that's no problem. We can do that. Paul and I agreed. We told them, we'll take your contract. That one is down here. This was awful. So this was a lot of years and a lot of misery about trying to make that mirror because it's so low on the yield curve. But all this data existed before we took that contract. Okay. So this is the mirror. This is actually an interferometric microscope image of the mirror. I had a student, Kara Silver, who sat in front of the interferometer and figured out how to both shape the mirror and record those things and make it into a movie. So this was her summer project, and I use it all the time, so I love it. I'm going to tell you about 3 applications in pretty quick sequence here. So now we've got the mirrors. What are we going to do with them? So I'm going to tell you about astronomy, vision science, this retinal imaging, and then a little bit about microscopy. So astronomy, my guy, Galileo, 1610, points the telescope up. Another thing, everybody knows that Galileo wasn't the first guy with the telescope. There were other people in and around the Florence and Padua area who had telescopes. What's different about Galileo is he's the first one that pointed up. So everybody else is looking over, look at that guy. So when he looked up, this was what he saw. This is Saturn, and we know that because we recreated the telescope. So we got the optics. This is what he saw in Saturn. That's got to be thrilling because nobody knows Saturn has rings. So this was exciting, and this really launched the whole field of astronomy. This is the Keck telescope, for which you paid about $75 million. It probably cost $1 billion today. It's a 10-meter telescope, segmented telescope. Here it is up here. You see a little guy in the bottom here waving, right? So this is a big telescope. And here's the quality of Neptune from the Keck. Now, if you're the guy who's got to go make the case that you've really, really outdone Galileo, this is not good. And this is 390 years later, right? So then they put the adaptive optics on, and they did get the improvement, right? So the adaptive optics fixes the aberrations in the atmosphere, and then a few years later, the quality just got better and better. So this is Neptune, or Jupiter from what they call the Very Large Telescope. They're not very creative about these telescope names. Very Large Telescope. Yeah, that's it. Okay. So then people took our mirror, and this one entrepreneur guy said, I want to make $1 million add-on to little telescopes. It's $1 million, is that right? Roughly. $1 million add-on, and so he made this $1 million add-on, and you can tell me whether this is worth $1 million for you. I'm not so sure. But this is the RoboAyo add-on, and that was maybe the second application of MEMS deformable mirrors for large telescopes. Then we had my friend Sup Chakrabarty said, if you could do this on the ground, I could do it in space. And so we got a grant from NASA to make a rocket that goes up, stays up for 8 minutes, looks at a planet near a star. When we proposed it, it would have been the first light given to an imaging system from a planet. And then comes back to Earth. So it seemed like a great thing. Got delayed a little bit, and then when it finally launched, I'm saying it worked great. But the thing is, none of the telemetry worked. So none of the data got back, and then it crashed. So I say the mirror worked well. I say it imaged the planet. But that's sort of a Schrodinger kind of thing at this point. This is though, what happened in between when we first proposed that and now is some people using real telescopes found planets around the HR 8799 solar system. 3 planets rotating around that thing. That was cool. And so suddenly that whole astronomy field turned to want to do this. They want to find planets. Why do we want to find planets? We want to know if we're alone. So the people from Gemini telescope contacted us, and they got a team together to build a Gemini planet imager that relied on a critical component, this 4,000 actuator DM from Boston Micro Machines. Here's that instrument being shipped to Gemini just this year. The expected first light is October 2013 on this one. So this is what we expect to see with the Gemini Planet Imager in comparison to what we've already gotten on the Keck. So it's better. What's hard about looking at a planet? This light down here that you see, this little blue blip, that's the light from the planet. This is intensity in log scale. And this is the light from the star nearby the planet. If everything were perfect. If everything's perfect, it's only several, maybe 6 orders of magnitude lower in intensity than the starlight that's swamping it. So these guys, these astronomer instrument people are great. They came up with an idea about how to use interferometry to null an area right around the star, block the starlight, perfect wavefront correction, and by God, the little planet will stick up out proud of the telescope, of the solar light. So when I got to BU, these were the planets. I think Pluto's not on there. We were predicting that it wouldn't last, right? So these are the planets in terms of mass equivalent Jupiters. So this is equivalent Earths. This is equivalent Earths. And semi-major axis, this is distance from its sun in atomic units, in Earth orbit. Astronomical, thank you. Atomic units, right. This is 2012. Thanks, Ted. This is 2012, all the planets that we know. And what's interesting is they're all different ways we find them. We can find them because the star wiggles. We can find them because the planet blocks the starlight a little bit, so it has a dip. But the ones in orange are special. Those are ones where we got light from the planet. So why is that important? If you can't get light from the planet that you distinguish from the star, you can't tell if there's life on it. You have to do spectroscopy to see whether there's life on it. So these are the only ones we can really tell anything about biologically. And with the GPI, this is what we expect. So we expect to get a lot closer. This is now in masses in Jupiters. And we expect to get a lot of Jupiter-like planets. So all this seems great. And so we built the mirror, and we gave them the engineering mirrors, and they had a couple of dead actuators in the 4000, and we said, here it is. And they said, well, here's the difference between a perfect mirror and one with one non-functioning actuator in this null we're trying to get. This is what your one non-functioning actuator does. So this made it much harder for us. And suffice it to say that we delivered something that finally satisfied them. I won't say it was perfect, but we made an engineering mirror, we made the final mirror, and that thing's going to give us first light in October. Bunch of other observatories have mirrors from us, and so this is one of our key areas of achievement in deformable mirrors. I want to go to vision science. First thing we did in vision science was we stuck a mirror in a 4-opter, in this thing where you're looking at the eye chart, and this was with the help of Livermore, we built this instrument. You stick your head in it, you see a little tiny eye chart, and it tells you automatically what's wrong with your eyes and fixes it. So look at that, you've got perfect vision. So this thing replaced what's in your optometrist's office, you know, the little thing where you say better or worse. And that thing cost $3,000. This cost $3 million. We didn't sell any of those. But as Ken was fond of saying, I won these R&D awards. When you win an R&D 100 award, it means you have screwed up. You've gone down a blind alley. So I've gotten 3 of them with BMC. So in the past decade, there's been some fairly transformative things in retinal imaging, just like there were in astronomy. So this was in 1996, the best image of a retina in vivo ever made by a guy named Don Miller, who's a great optical instrument developer. This is without AO. This is the first image with AO by David Williams. David Williams up at Rochester, and then things are getting a lot better in that field. So what did we do? We saw everybody using our mirrors to make these retinal imaging systems and nobody putting them in the clinic. So what Paul did was said, I have to make one of these instruments, not because I want to learn how to make the instrument, because I want to get one to the clinic. I don't want to play with the instrument. So this is what a normal ophthalmoscope will do, what it'll give you as an image of the retina. And what we did was built an instrument, had it built with taking the best features out of all the instruments that had used our mirrors in the past, and we got a much better image. And then we took that instrument, and well, first I'll show you some images. So this is an image from my friend Austin Rorda, where we're sectioning through the retina. So when you see these striations, okay, we'll wait. These little dots, those are your cone photoreceptors. The black things, of course, are blood vessels. You can see the blood flowing through the blood vessels. And then these striations are your nerve fibers. So those are above. Those are above the photoreceptors. Again, the blood vessels are above the photoreceptors. And so you could see very clearly the cellular structures in the eye. With our instrument, we were able to see this nerve fiber layer. We were able to see the cone photoreceptors, and we were able to see for the first time microaneurysms in the eye. So these are things very related to disease. So this thing was powerful. Once we knew that it worked, we sent it to Joslin Diabetes Center, and all we were was support from then on. They decided what to do with the instrument. They stuck it in clinical. It's back here. I took my class to see it. This is my class. But we stuck it in there, and we support it. And then and make sure all the images are good, but they're using it in clinical trials for drug discovery for diabetic retinopathy. Okay, last subject, microscopes. So Thorlabs loves these mirrors. They sell them in their catalog. They love the mirrors. So they decided to make an instrument, this wide field microscope. When you have a microscope and you make it high resolution, I'm going to look at high resolution. What happens? Your field of view shrinks. It always shrinks. Why does it shrink? Well, because it's expensive to make a wide field objective. That's all. It's not impossible, it's just expensive. So Thorlabs had this idea, let's make a wide field objective and make it badly. And then use the deformable mirror to fix the objective wherever wherever we're going through it. So I can fix it. If I'm looking over in that angle, I fix it. If I'm looking over this angle, I fix it. So they made this thing. It's very beautiful. It can look at, like this is a mosquito larvae, and you get 1 micron resolution over, tens of thousands of micron field. So it's everything's great. I mean, everything's wonderful here. Didn't sell very many of these. Apparently, this is not as interesting to other people as it was to us. So, but this is the kind of thing that they were doing with the microscopy. So we started getting interested in other things. I had a conversation with Jerome, and we decided we would try to image through strongly scattering media. Because this is the challenge of imaging in the brain, and that seems like one of the places where there's really not been a lot of progress so far. So we started down this path, and we said, Jerome gave me the tutorial. So these are Jerome's slides. If there's any mistakes, Jerome is right there. In a scattering medium, the beam spreads. So I'm trying to focus the beam. I can't focus it because it spreads due to the scatter, right? And at the far field, I get speckle. So there's just all these blobs of light. And it gets worse the deeper I go, the more modes there are, the more speckles there are. So we didn't discover, other people discovered that with a spatial light modulator, you could precondition the light so that it had constructive interference in these speckles so that the central speckle was brighter than the rest of them. And that looks a lot like focusing. It isn't focusing, it's constructive interference. But it looked enough like focusing, so there were a ton of papers in Nature and Science saying this thing is really magic. And when we looked at it, we realized it wasn't all that magic, but it was a great application for a DM, so we're in. And so we took the spatial light modulator, and we built a little system that would try to go through these scattering media. And what we found, if you look at this slide, the left side is the speckle pattern. And you notice its intensity goes from 0 to 3, just in arbitrary units. The right side is scaled to the same value, and it goes from 0 to 600, and you get this very bright spot. So you're 600 times brighter at that one speckle just by optimizing this system. We use this segmented DM to make this work. Here's I'm going to impose a bunch of shapes on the SLM. I'm going to watch the optimization happen. What's the enhancement? And I'm going to watch in this, what looks like a pretty dark field, watch the spot appear. So you can see as I do my optimization, the spot gets brighter. And then when I'm all done, this is the shape in phase on the SLM. So it doesn't look anything like focus or anything like that. It's just constructively interfering to give me a beautiful image. So what do we do with that? Well, of course, we think about the guys who pay the bills. The first thing we do is send through and write BU through the scattering medium onto the camera. So we can, even though you can't really get a sharp point on that camera with anything but the SLM, we can now write BU on there. Jerome was unimpressed. So he says, let's try to optimize through biological media. We tried that, so now we had a little bit of chicken, and the chicken is sagging and oozing, and we're going through it, and we then move the spatial light modulator, and we're able to control, optimize, until we turn the control off, and it unoptimizes again. So we had some capability of doing dynamics. The problem is, to make this work, you need a camera deep in the tissue. That's a mess. That doesn't work out so well. So Jerome and others had an idea, actually, and I think the idea may have first been published at Genelia Farms, HHMI. You could do this technique with 2-photon microscopy, because 2-photon gives you a signal that looks like it's coming from a camera deep within the tissue. So we set about to do that, and we didn't want to build our own 2-photon microscope, so we borrowed one from Thorlabs. They gave us a 2-photon microscope setup, and here it is. Here's the first light, which is about a month ago, and this is the system correcting for this spherical aberration, and sure enough, it improves the signal. So this is where our research goes now. Okay. That's it. That's it. So here's the conclusion are, we got all sorts of capabilities with these MEMS mirrors. I really haven't done a lot in recent times on design. That goes mostly to BMC, and we've just started a new set of manufacturing problems with MEMS mirrors. I'd like to thank a whole bunch of collaborators. I won't mention all their names here, but there's a bunch at BU, there's a bunch of students, and all the staff at BMC, and I acknowledge a financial interest, in case you didn't know, in Boston Micro Machines Corporation. I'm grateful to all the founding funding agencies. Thank you.
Well, I'm sure we have some time for some questions for Tom, if there's any.
Yeah.
Ron?
Tom, how deep can you go with the 2 photons, and what size are you talking about?
We think we can go twice as deep. The person who did this, it depends on the scattering mean free path and the transport mean free path in the sample.
Well, let's say you're talking about chicken.
So let's go back to brain. So normally in brain you can go half a millimeter. That's pretty reasonable, and we're hoping to go a millimeter.
Okay.
And if you do that, there's actually, it's like the vision science thing. If you do that, you suddenly get through a significant functional section of the brain that you wanted to see. Going deeper would be better, but the difference between a half a millimeter and a millimeter is substantial.
Is that also spot size you're looking at as well, about a millimeter?
Spot size. Spot size is, well, it's the scan. There's a scan area, field of view, and the spot size. Spot size of the objective is a micron or less, and the field of view is probably 20 or 30 microns, no more. It's very small. This is looking through a tube. Yeah.
Is there a desire to increase the mirror count, and what is a practical limit in your view?
Is there a desire? That manufacturing problem was hard. There is a desire to go bigger. The next generation of what they call, what is it, overwhelmingly large telescope, you know, another bad name. The overwhelmingly large telescope is going to need 100 by 100 or 10,000 actuators. In most applications, other than planet finding, a few dead actuators are no problem. If that's the case, that desire we can meet. But I think to make them perfect with 4,000 actuators, that's a hard job, and I don't think we have an answer about how to do that well yet. Does that answer your question? Yeah, Bennett?
Is there any also desire to make them really cheap and pervasive? And could you imagine them in
So
everything from iPhones to everything?
iPhones probably not. So the cheapest mirrors we make, the most affordable mirrors we make, are about $5,000 or $7,000 for 32 actuators. You bought one, actually, and yeah, that's right. Oh, right, that's right, 15,000, and but they could be much less expensive. The biggest expense is the driver. So the driver is you've got a driver that's running at 200 or 300 volts at a few kilohertz and N channels. So with the 1,000 actuator device, that thing ends up costing about $150,000. They sell them pretty good at that. But yes, there is actually a current program at BMC to try to, in cases where you can phase wrap and you don't need as much voltage, to make them much, much less expensive, and there's a target market for that. Yeah, Glenn?
So is price the reason you're not making deformable mirror eyeglasses?
Yes. Yeah, well, the other thing is you'd only see your own face, right? So they're not transparent. And yeah. Oh, yeah, so you could have the tilt-up glasses, right, so at an angle. Every day Paul gets lots of inquiries from people who want an application that'll get lots of these for very little money. And in fact, the Center for Adaptive Optics, which helped us quite a bit over the years and was an NSF S&T center, used to always say at the beginning of every meeting, we're aiming to make these MEMS devices cost a penny an actuator. And it always caused us a little chuckle. Yeah, Ted.
Piezoelectric actuators, any...
So piezoelectric actuators are not native to the sort of fabrication that's done for MEMS, silicon and silicon dioxide. So all the competitors who went with piezoelectric lost in the end because they couldn't use a foundry. We save a lot of money by using a foundry. Even though the foundry costs are high, they absorb lots of the capital costs. So that was one failure. The second failure is that piezoelectrics, no matter how well they're made, they creep and they don't stay in the same place. So you can never do open loop control. As it turns out, for astronomy, the next big application is something like tomography, where the telescope is so large, it's looking through different parts of the atmosphere. And so for that, you can't actually, you can't have a feedback loop in the traditional sense. You have to measure the wavefront and put that on the DM, but you don't know how well you did. In that case, piezos can't work at all, so they're relying on MEMS mirrors, which is good for us. Yeah.
Is there any way of hybridizing the kind of technology that goes into DLP kind of things with this to get cheaper and also get beyond the limitations of them, which is simply on-off?
Yes. So we did that. We made 150,000 actuators on CMOS with Alan. Alan, do you remember that project? There was Alan helped us with the VLSI. We made them on the CMOS. We were doing this at the chip level. So we would make CMOS chips and then process the MEMS on a chip. This was a bad idea. 2 students got their PhDs from it, so I won't say that it was, an outrageously bad idea, but it never had the chance of surviving as a manufacturable process. But there's a group at Fraunhofer in Germany that makes such mirrors with segments that move up and down, and that works, that you can make that work. It's unclear that there's a really giant market for that, though, and there's a big capital expense.
So in the beginning, I thought you almost answered my question right there, but then actually in the end, you said something that maybe revived my question. How do you view competition with SLMs? Are SLMs going to take over? Are they creeping into what a DM can do, or can DMs creep into what SLMs can do? And then
so
the question
difference is, so in an SLM, which is just a spatial light modulator, so piston element segmented mirror, we have trouble getting to large numbers. So we can't do a Hamamatsu SLM or Boulder nonlinear SLM can have 1 million pixels. I won't say never, but it's unlikely we're going to get to 1 million pixels. On the other hand, we can go at 30 kilohertz frame rate. An SLM at best goes 30 hertz frame rate. So when you think about the degrees of freedom you can change per second, we beat them on a lot of measures. So we do quite well. And there are many people in this microscopy field who are anxious to have spatial light modulators that are not wavelength dependent, not polarization dependent, and super fast. So yes, I think this is a great big market for us. Yeah.
Okay, I want to thank Tom again for a tremendous talk. Everybody stay seated. We've got 2 gifts for Tom so he can remember this talk and this moment for the rest of his life, or at least through the remainder of the evening. And they'll pick an hour or so to get in here. The first is an endowed wooden chair.
Nice. Oh, thank you.
And
so nice.
It has my name on it.
That's right. It says Chairman Biomedical.
Right. And this is a chair he can rest in as he ages. And the other one is a framed version of the photograph and the announcement of this wonderful talk that Tom has given.
Thank you so much.
Yeah.